And I think we can now start our panel discussion. So I ask all the speakers to be back and to participants to add question in the chat. So like while listening to your amazing talk, I think what I was like finding as a sort of overarching topics is complexity. Complexity can be complexity in the robot body, complexity in the brain, also trying to, let's say, divide timpera, like, or trying for example, to distribute, let's say, complexity in different part of the body. So the question that like I have is, what is the balance between brain complexities versus body complexity, especially when we have to deal also with the complexity of the environment, like for example, the scenario that Tommaso was showing, and how we should so balance these two. Should we put our effort in like simplifying the aspect of, let's say, the brain complexity and moving toward more complex body's morphology, or like having a different approach on this. So I don't know who want to maybe start, or if you have any idea on this topic.
I guess I can start maybe. This is such a good question. Thanks Perla, and it's very interesting because I'm thinking about the medical application, for example. It's a very constrained kind of environment somehow, and it's interesting to start introducing complexity of the body to sort of address the complexity of the environment. So the heart is as complex as you can get in terms of, like, dynamic environment, so on and so forth. So the inherent compliance and the material properties of the robot become critical in being able to navigate that. But on the other hand, you don't want to relegate everything to the body, because you still have a very sort of delicate organs you're working with, and there are so many ways in which that can go wrong. So this is actually an interesting point, because it's a point where we're struggling, and we're sort of discussing this actively with our clinical collaborators. Like, so how much of the robot should only deal with the heart motion? How much should we add sensing to sort of monitor that? So the approach we're sort of converging towards is, let's trust that the robot will do that, but let's put some additional sensors and some sort of safe methods to act in case something is going wrong, or to make sure that we can monitor things appropriately. So it's a difficult balance, definitely to strike between the two. I think again, what we're striving towards is using active control or brain as a supervision of the body. Let's say.
Yeah. Now I think like there is of course also a problem of like limitation in how much complexity we can put at the moment, technologically speaking, in the robot body, of course. And I was very interested in the work of Rika, that was like the robot was like creating his own tools, and so like increasing its complexity in a way, but using his brain to think about how to like change its morphology to deal with the task at hand, and that probably show more like intelligence in the brain, I guess, like in figuring out like how the body can be augmented in a way such that we can increase like the complexity of the body at end. So that it was like very interesting, again, balance between the two, body and brain, and also the work of Jeff. Like I was interested in like you were discussing instead on the aspect of simple networks. So at a certain point, there is no much benefit in increasing the complexity of the brain. So how do you instead like see this difference between body and brain complexity, and how maybe the brain can leverage complexity of the body to deal with the complexity of the environment.
Yeah, so I mean, just to kind of address your previous question about how much complexity is necessary, it really depends, I guess, as Tommaso was saying, on the task, on the complexity of the task and what we're trying to do. So, I mean, for cases like his work, it's very difficult to evolutionary design and simulation and then transfer it to actually a real physical entity, right? So, but that is one key idea. So we basically try to have some form of evolutionary design, which in simulation can then be transferred to a counterpart real world system. So we basically try to emulate natural evolution is what I'm saying, because every body brain coupling out there has evolved specifically for its environmental niche, right? And it's perfectly suited for survival in its environmental niche. But for these new tasks, we are constantly trying to tackle and solve. It's a challenge to even try and decide what form of morphology there should be and what the underlying neural complexity should be. So I think evolutionary design can certainly help a lot in, at the very least, optimizing the design of these systems. And I think as we move more towards physical embodied systems, then we can do things like what Brad Nelson was showing with these surrogate phantom entities that basically stand in for the real world organ or surgery or whatever we're trying to do. But yeah, so I think there's no clear answer, unfortunately, but it really depends on the type of task we're trying to solve. And yeah, in terms of simplicity of the networks, this is something that we see in the world of social insects. So they tend to have very simple networks, but it is the interaction of those networks that produces complexity overall, and that seems to be a key because it enables them to have a very low cost in terms of energy they use, but it also gives them all of the advantages of working in social groups, of redundancy, robustness, and all that type of thing. But yeah, but then of course, I think you're also asking about why we're social creatures, why we have such complex brains, and they're very expensive to run. So that goes back to the social brain hypothesis, but I think there's no clear answer to that yet.
Yeah, that is, I think, a difficult balance. I'm actually interested also, I mean, since you mentioned the social aspect about the work of Mihoko. I mean, you discuss about like the complexity of social interaction, let's say through the conversation. Did you see a difficult, I mean, like, I think in your study you were more like looking at like the conversation, but how much of the body is involved in this, or how communication complexity is distributed between just like the brain and the body.
Yeah, thank you very much. And so in terms of complexity, so vocabulary richness reflects a kind of complexity of the, thinking activities. And so, in terms of, brain and body, and brain itself is also a part of body in terms of interaction. So if the through interaction, we can change our brain. And so because brain is a part of body, and then so through the usage of brain changes the structure of the brain. So we cannot divide body and brain in terms of this situation. And so, and in terms of complexity, I found through the discussion that the brain reflects complexity of environment and the body. And so in interaction with the environment, including other people, may, change. So the complexity of external world influence the internal complexity of the brain. And so if there is a kind of enough interaction with the environment and the person, And so, the complexity of the brain may be maintained. While so if there's less interaction or less openness to environment, and then so the complexity may become less in the brain and the brain structure or brain networks, and which may decrease the functioning of the brain. So in terms of balancing the complexity of brain and body, but so I think the openness of the system may change the complexity of internal system and external system. So, so if the system is flexible enough or open enough, and then the complexity may balance within the between environment or internal state. So if for example, soft materials or soft body or exists and they interact with the surrounding environment, and then finally the structure of the soft body or material will become very complex through the kind of motions or interactions with the environment, and this may also may have some connection with Rika's work on simulation of soft bodies, and then so interaction with the environment, and then so differential simulation of interaction with the external environment. So somehow we have not yet simulated our brain functioning yet, especially in terms of conversation. But I'm now thinking of how can we simulate such process like Rika's work. So this is my maybe or very big challenge. But yeah, I really through the interaction with other talks and in my brain. And so I found some possibility of such simulation, as well as how we can change our complexity of ourself or maintain our complexity. And so that's important to maintain our living, I think. Yeah, so sorry that my work is really different from others' work, but so through some kind of, analogy, yeah, I hit upon many ideas through the talks. Thank you very much.
I think like also in your work there is some like sort of let's say balance between the body and the mind. So, and also I mean I think the link to Rika, I mean you were trying to shape the morphology or model the behavior, the interaction behavior through your differential simulators, and like how can you are you thinking maybe to include in your optimization also aspect about like the balance between the control and the body morphology, and so co-optimize the two?
Yes, that's obviously a very good point to wonder about, because as a learning person, right, I would immediately want to do some sort of a co-evolution, co-optimization. This is very tempting to do from basically day zero. Interestingly, what we found is that such problems are a lot harder than they are usually made out to be. So basically, the issue is that you can get into this kind of interesting, difficult spirals where if you allow both the morphology and the policy to be optimized, then it is not immediately clear for what morphology should the policy be optimal, and for what policy should the morphology kind of like adapt. And you would think that basically it's like, in the learning, you can tweak some sort of learning rates, you can do some sort of a curriculum learning or something like this. But it's actually a bit tricky to do this, especially if you have like crazy optimization landscapes that I've shown. So I really think that, it would be good to, keep on communicating with people from, the evolutionary side of things and the black box optimization, because I think, gradient only techniques, sometimes we sort of might overestimate the power of what they can do. So the complexity kind of when it goes beyond what a single gradient method can handle, one really needs to bring a variety of methods and combine them. Yeah. To touch upon a little bit what Mihoka was talking about, how to bring in sort of the social interaction, the complexity of the brain and so on into simulation, that is extremely challenging, right? Like once again, your complexity of the system goes up, then it is basically difficult to understand whether the prior that you put in, meaning kind of the model, now it's physical and biological like all together, right? Whether that has the correct prior or whether that is something that maybe had under modeling, and so you would kind of skew the results because of that. So that's extremely challenging, but that's research. So I think these are like all very much open frontiers. Yeah, and I think definitely the co-optimization is something that's very interesting. I was thinking actually about this continuum between adapting the mind and adapting the body, and like what Perla, what you pointed out, that tools is something in between, right? It is not really a part of your body. At the same time, when you grasp it, when you hold it, when you are operating with it, it is an extension of your body. So it becomes your sort of part of your morphology for the time being. And so, but at the same time, it is very quick to exchange. And so that's why the optimization for that can actually iterate a lot quicker than, let's say, optimization for your body as a robot. So maybe there are other kind of points that we can find along this line of, body versus mind optimization, where there's something in between and not one or the other, and that might, create new opportunities.
Yeah, this is a really really good direction for future for all of us to follow. I was like looking if in the chat we have some question maybe on the line, and there is like a question from Josie. For collective intelligence, do we want homogeneity or heterogeneity in the individual? For social embodied intelligence or physical embodied intelligence? So this is like, I mean, I think probably we were discussing before, like as Jeff was like pointing out, like having intelligence emerging from like individuals. Do we need them to be all the same, or are we thinking about like different kind of individual? What is the
So
best?
I can have a go at that. So that's a really great question. So if you're looking at the evolution of neuromorphology in social insects, you see heterogeneity, right? Quite often. So you see like the workers versus the defenders of the nest, and they have very different morphologies because they have very different specialized skill sets. And this makes sense because of the physical tasks that they basically have to do over the course of their lifetime. But when you look at mammals like us and our closest genetic cousins, we basically all have the same morphology, but the morphology is general enough to elicit a whole range of really diverse behaviors to basically solve any task we want to solve in our given environment. So it's, once again, it kind of depends on the ecological environmental niche as to how these evolve. But one could argue that if you have a general enough morphology that encapsulates sufficient neural complexity, then you will be able to solve any task that you are given or could come across in your environment. But I think that is the challenge of everything we've seen thus far, right? It's not just like the morphology, but the materials that go into the morphology, the construction of the morphology. It is really difficult to define some kind of morphology that works well for a broad range of tasks. And I think that's the ongoing challenge here.
Yeah, definitely, like to be able to, we need to actually put the environment in the loop as even like for these particular things. And again, our optimization function should also include that. And also, I think another question, I mean, again, what parallels can be make between social and physical embodied intelligence, I think like that is something maybe partially we also answered. I don't know if some of you want to again reiterate on this point.
I
Yeah,
guess.
so
Oh, yeah, go ahead.
yeah.
I was going to say, actually, to clarify a bit the question, because one could ask kind of how far the control of the agent extends, right? If I am just controlling my arm or my hand, okay, that's clearly me controlling myself and physical intelligence. At the same time, if I'm telling somebody to do something, that is sort of a social intelligence. You know, I have to convince them to do it. I have to explain how to do it and so on. So I think this is one of the sort of clarification of maybe not necessarily parallels, but it's kind of where does the body stop and where does the social aspect begin, even though, you know, our bodies are separated, right? It's kind of like guiding somebody, showing somebody, this is something like more hands-on than just talking to them. So that's an interesting thing. Maybe Mihaku can expand on that.
But it can be also an extension of ourselves in a way. Like, I mean, if I cannot do something, I can ask someone else to do it. So it becomes like it's extending my morphology through like someone else in a way, morphology, or like, let's say, achieving collective intelligence through different individuals. So that is maybe linking like this like aspect of identifying capabilities that can be used to achieve a certain task or goal, and so
Yeah,
maybe
yeah.
the parallel can be there, of course.
Yeah, in terms of homogeneity and so heterogeneity, I think heterogeneity is necessary in terms of complexity maintenance, because homogeneity, agents interact with each other, but the complexity may not increase, while heterogeneity engender interaction, and then both complexity increases. And so in terms of maintaining complexity, heterogeneity is really important, I think. So that's and so especially for social interaction aspects, so heterogeneity is a kind of must for, so enough, improvement of interaction, I think.
Interesting. Also, this like point of view, of course. I think Jeff White wrote, one idea that came up in the morning was that embodied agents learn best from similarly embodied agents, as what is seen translates into personal action, two common embodied dynamics. I think it is more a statement than a question, but I don't know if, like, again, some of you want to comment on that.
That's true. I think to the extent that there is progress being made by the similarly embodied agents, and I think probably everybody can comment in the same way. When you hit the limit of that, when you hit a roadblock where with the given morphology you cannot solve the task, that is exactly where you kind of like hit this local optimum, and then you cannot go further. And it's actually a bit difficult to anticipate that point, again, because if you have homogeneous agents, they tend to eventually converge to, you know, maybe slightly different, but still not so substantially different ways of solving the task, and then you're kind of stuck. So that's, but at the same time, yes, you have the sort of economies of scale, so to speak, right? Like you can collect more data, you can share, you know, knowledge, approaches, and observations, and all that, and you don't have the embodiment gap. So yeah.
Okay, I think I don't see any more questions from the audience so far. And I think, so, I mean, like Fumia just like wrote a question about not much discussion about AI, machine learning, GPT, and LLM. Any comments on this? So.
I comment on that. So I think the whole AI revolution, as it's called or being called, is vastly oversold. And I think others have even mentioned there is a very low ceiling in terms of what ChatGPT and its imitators can solve because it doesn't have a body. It is not embodied, but it's trained on, yes, our data, which comes from embodiment, but I mean, it's extremely limited just by being trained on that data. So it's limited by its own data sets, which is its world that it can see, and that has, yeah, serious constraints on what it can do. But I think others have said more or less the same.
Any other?
Yeah, I can comment a bit on that too. So one aspect is I fully agree with what Jeff said, and especially now, like I have a few recent works that try to look into LLMs, and I, like know very much their shortcomings. One of the interesting things, though, that came with this hype is sort of, again, now here are the economies of scale. And surprisingly, there is this humanoids bandwagon that people are jumping on. And there are like dozens and dozens of companies that are for real making humanoids that are actually operational. And there, interestingly, it seems like it's like quantity, like quality might actually transition into quality because they're iterating on the designs. They will be driving up the demand for, sensors, hardware, motors, all that stuff, right? But also they're sort of bringing in the other big players like NVIDIA, for example, who's recently announced that they're doing foundation models for, humanoids and so on. So because there was this not entirely kind of hype that was not entirely kind of full of substance, things were a bit maybe problematic at the beginning, but at the same time, because there is like this enormous amount of interest, eventually even things like, doing robotics in the industry started being like humanoids, started being sort of possible, right? And so this is one of the things that can actually shift things substantially. If indeed, the startups don't dissolve and the money doesn't disappear before some actual, real advances are made, we might gain like a big step forward in terms of what the hardware can do and what amount of data and compute has been spent on putting together the basic kind of functioning models, learning models, AI, machine learning, RL, for that. So actually, we're talking quite a bit in groups that work on, let's say, everyday tasks or things that maybe humanoids can address. And there is a sense that with enough data and with enough compute, one could actually kind of go beyond the weaknesses of what the current LLMs have. And then it's not going to be LLMs only, right? It's going to, of course, gonna have vision as part of it. And then eventually the big question is whether sensing will be necessary or not for this. Sensing in a sense of, tactile sensing as some sort of force information, something beyond just only the visual inputs. So we'll see about that.
Yeah, that's a quite interesting aspect. Of course, like most of the time we are limited by the energy and resources, computational resources we have on board of these robots. So especially when we want to deploy them in difficult environment, or for example, what like Tommaso was saying, when you have like environment where you need to have systems that are trustworthy and like you need to be able to debug what's going on for a safety reason. Of course, that like pose a quite huge limitation on the use of this system and in future, especially for robots that needs to operate like let's say in the wild for long. So I mean, I think that's of course limit their so they can achieve like of course like huge capabilities, but I think this is quite a big limitation we have so far. So I mean, what I presented also was trying to compute a small logic function within the robot with respect to the complexity of LLM or the GPT. I mean, to enable robot to maybe stay, I don't know, in the wild, collect information or perform operation in environment where, of course, that kind of energy or computational resources are not available. So and it's a little bit, in my opinion, something we need to consider. I mean, we want we are pushing toward these systems to make them be able to cope with very difficult environment, but potentially we have to place in an environment where the resources that are needed to run the system are not available. Or so it's like, in my opinion, something to consider on this respect. I mean, very, very excited like about the things, but I think we need to have still this in mind.
I actually agree so much with you, Perla, on this. Actually, so I think there's a lot of potential in applying. For example, we're working a lot on applying like ML for like control of soft robots, but to be able again to operate in complex environment, to adapt. But there's all still when we bring in more body into the equation, there is that means that we're bringing, you know, like a lot of hardware complexity, which ties into a lot of problems in terms of like, I know I've seen you, I'm quite familiar, for example, with your work, Perla, on like onboard control. We're also doing some work on that area as well. So like, how can we, for example, if you make your body entirely soft, and then how can you ensure that it can operate independently from like a lot of like pressure controller pumps and all this kind of things? So how can you actually deploy it into the wild to be able to collect the necessary data and perform complex tasks? And I think there's still a lot of I do agree there's still a lot of hardware challenges that need to be addressed. How can we make the actuator reliable enough to operate for thousands of cycles, sensors reliable enough to operate for thousands of cycles, that are necessary then to apply more of these data-driven approaches? And this is something that we've been starting to have some good success, but I think there's a lot of work to still be done, and those are critical challenges then to that we need to address to actually be able to deploy the system in the real world and collect the number of data that we need to implement these algorithms.
I think also another question I have is like about the limitation, how the body limit what can be achieved by the brain. I mean, of course, like we move, we interact with the physical limitation we have that are our body morphology. So again, like environment, we discussed with Geoff like the environment and how the complex environment maybe lead to the development of the brain. And I think also like the balance is also in like how the limitation of the body limits like the capabilities of these systems. To a certain point, like you interact and you move with your own, and you sense with what you have on your body morphology. So that is the other aspect that like I think it's interesting to consider. I see Josie, don't know like if this means like okay, that this is the close of the session. I mean, I think I want to thank you all for this amazing panel discussion and for all your insight on this. And again, thank you, Josie, as well, to invite me with Fumia to this event.
Just to say thank you, a huge thank you to Perla for hosting this session, and to all of the speakers. I think it was, despite the diversity in topics and all the different opinions, I think it's really interesting how we can come together and have these kind of fundamental kind of agreements on where things can be going. So I think it's great to have these discussions. So thank you, Perla, to doing this, and thank you very much to all our panelists. I think some really interesting insights from these kind of cross-disciplinary perspectives. So thank you very much. So that finishes